Hey everyone, and welcome to today's video where we will be talking about Ladybug and Honeybee. So if you're an architect or urban planner looking to integrate sustainability in your design process, this video is for you. So Ladybug and Honeybee are both part of the Ladybug Tools suite, and they are both plugins to Grasshopper, allowing you to visualize environmental data such as solar radiation, daylight analysis, and energy performance right in your design process in Rhino and Grasshopper. So this makes it easier to make informed decisions early on, leading to more sustainable and high-performing buildings and plants. Now, this software can be very complex, and I'm not going to cover everything, but I'll highlight the key features that I as an architect have found most useful in my workflow. So by the end of this video, you'll have a solid understanding on how you can use these tools to evaluate your designs for things like energy performance, thermal comfort, and daylight performance. So without any further ado, let's jump into this tutorial and let's get started. So before we jump into Grasshopper, make sure you have the Ladybug plugins installed. You find them here in Food for Rhino. So you simply just download the version that you want. I would recommend downloading the latest version. And also make sure you have these tools that are compatible with the version of Ladybug that you install. So for example, I'm using the latest 1.8 version. Then I need to have these versions of Radiance installed, these versions of OpenStudio, and so on and so on. So just make sure you have all these before we jump into Grasshopper, so that everything will run smooth and you won't get any errors. Okay guys, so here we are in our Grasshopper viewport. We have our, let me increase this a bit. We have our Honeybee submenu here. We have our Ladybug submenu. We have our Honeybee Radiance, our Honeybee Energy, and so on. But before we do anything, let's go to the Ladybug submenu. And we actually first need to import a file containing the climate data about our site. So to do that, we can use this Ladybug EPW map component. And what it needs is, it needs a Boolean toggle. So let's connect a Boolean toggle to it and set this to true. And it will actually open a new tab in our browser to this map with all these files containing climate data about sites all over the world. So let me zoom into the location where I'm currently at. So I'm going to use this file from Stockholm Arlanda Airport containing climate data about Stockholm, and copy this, go back to Rhino and paste this link into a panel. And then I can use this download weather component, connect this link to the weather URL, and I will get an EPW file, a stat file, and a DDY file from this component. And then I can use the EPW file, connect it to an import EPW component, and then I will get all this data about my site. And with this, I can use something like a deconstruct data component. And for example, I can deconstruct this data into a list of values of the temperature, and then I can use something like an average component in order to see what's the average temperature in Stockholm all over the year. Well, it's actually only 6 degrees. But I can also use something like an hourly plot to visualize this data in a more in a way that is telling us more, basically. So I will just connect the dry bulb temperature into the data input, and it will give me this diagram. Let me actually change this to rendered, and we can see what the temperature is in Stockholm throughout the year, from January to February or to December, from 12 a.m. to 12 a.m. So we can see that in summers it gets almost up to 30 degrees, while in winters it drops down to almost minus 20 degrees on its coldest days. And this can give us great insights about our site. Before we start designing anything, it will give us an idea on what type of site it is we are working with. We can also visualize, for example, the relative humidity or the wind speed or any of these outputs almost into our hourly plot. And then we can export this diagram as a mesh into Rhino, and that we can later continue working on in Illustrator or whatever software we want to use in it. So let's connect the temperature once again to this, and let's hide this and show you some other visualization tools that we can use. So we can also use something like a sun path. So let me go back to perspective mode, and what this needs is it just needs the location basically. So I'm just going to plug in the location. Whenever something is underlined before the text, it means that this input is required for this component to work. So this is how Ladybug and Honeybee components are working. So let me connect the location to this, and it will give us this model of a sun path showing us how the sun is moving in relation to our site. So each of these curves represents an hour basically. And I can also change what type of data I want to visualize in this component by using something like an analysis period component. So with this, I just need to set a start month, a end month, a start day, an end day, and a start hour and an end hour. So let me plug into, for example, the value of 6. Let's say I want to just see my sun, how it's moving in June, for example. So I'll plug this 6 into the start month and into the end month. And let's say I just want to see it on one day in June, maybe the 21st of June. I want to see how the sun is moving. So I'll plug this into the start day and into the end day, and then I'll plug this HOYS output into the HOYS input into my sun path component. And now here we see where the sun is on all these hours on this specific day, on this specific month. So it tells us that in June we actually have sun 19 hours of the day we have sunlight in June in Stockholm. But if I change this to January, for example, you will see that now we only have sun for 7 hours in the day. So what this sun path is telling us is that there's a huge difference between summers and winters in terms of daylight. So this can be very important to consider when we are designing our spaces. But let me hide this for now and also show you something else, because we can also visualize the wind of our side with something like a windrows. So what this needs is it needs the data, which is the wind speed, and it needs the wind direction as well. So I'll plug these two into my windrows component, and I can go back to the top view, and now you will see this diagram visualizing how the wind is moving on our site. So we see that most of the wind is coming from the south west, almost no wind is coming from the east, some wind is coming from the north, but overall it's not super windy. I would say it's relatively mild in terms of wind. It doesn't really go above 6 meters per second for most of the year. But this can be very important when we are designing our spaces in terms of natural ventilations and so on, how we place our windows. This type of information can be very useful. So this was some initial tools that we can use to get an idea of how the climate is in our site. Okay guys, so let me show you some more tools and components that we can use to visualize even more data about our site. But first let me group the components that we've used so far and put them over here. Let's give it a color. So first let me show you the sky dome component. So the sky dome, if I hover over it, it says visualize a sky matrix from the sky matrix component as a colored dome, subdivided into patches with a radiation value for each patch. So first I need to also create a sky matrix for this component to work. So let me do that. And what the sky matrix component needs is it needs the location, it needs the direct radiation, it needs the diffuse radiation, and that's it. So now I can connect this sky matrix into my sky dome, and this is what it looks like now. So this sky dome is telling me from where the sun is giving me the most energy. So this can be very useful when I am designing solar panels, or if I'm thinking about taking advantage of the solar heat gain with my windows in a building, for example. So it can kind of guide me in how to place my solar panels or my windows in order to achieve the most energy efficient solutions, basically. So this component can be very useful for those types of scenarios. Let's group this and hide it for now. And let me also show you the last component in this part of the video, where I will use something called an outdoor solar MRT. And MRT stands for mean radiant temperature. I'm sure you're all familiar with the feels like temperature concept, which takes into account not only the temperature but also things like humidity and wind and solar radiation, and gives you a more accurate feeling of what the temperature actually feels like. Well, this is something we can also generate in Ladybug and calculate with these climate data file. So what this component needs is it needs the location, it needs the temperature, the direct normal radiation, it needs the diffuse horizontal radiation, it needs the horizontal infrared radiation, and that's it. But it also needs a boolean to run this component. So I'll connect this and put this to true, and the output I get is an MRT output that I can use in UTCI comfort component. And what UTCI stands for is Universal Thermal Climate Index. So it needs the MRT, but it also needs the temperature, the humidity, the wind. So I can connect those outputs from this EPW file into 3 data containers. One for the temperature, one for the humidity, and one for the wind. And just connect the outputs to these containers. And then I'll drag these containers down to my UTCI component and connect them here. It also needs a boolean to run this, so I'll connect a boolean as well and put this to true. And with this output I can connect this to an hourly plot, for example, which will visualize when it is comfortable to be outside in Stockholm, basically. But I can also connect this to a comfort statistic component, which will give me a value of a specific value of how much in percentage of the time it is comfortable to be outside, how much it's too cold and how much it's too warm to be outside in Stockholm. But now it's taking into account all these factors. But let's say I want to see what it would be like if there is no wind. Then I can just disconnect this wind input, and now it actually increased to 40% of the time to be it's comfortable to be outside in Stockholm if there's no wind. If I disconnect the solar radiation, or the MRT, the mean radiant temperature, it actually increased to 45% of the time. So now it's also comfortable in these summer days when it wasn't comfortable before. So you can play around with these tools a bit and see. It gives you a great idea of what the outdoor conditions are like in your site. And it can really guide you in your design decisions when you are working on things like anything in terms of architecture and urban design. These tools can be very useful. So let me group these and hide it for now, and that was all these first initial components that we can use to get a first idea of what our site feels like and what it looks like, and give us some initial ideas on how we can design our spaces in order to achieve the best results. Okay, so here we have our 3D model of our building and our site. It's a very simplified version of our model. It is important when you're working in Ladybug and Honeybee that you keep your models very simple and clean in order for the tools to work correctly, basically. So let me show you a little bit about this model. I have the trees as these surfaces. You can make the trees, you don't have to make the trees, but you can have the trees if you want to add some realism to it. And you can also just make the trees as a simple sphere. It doesn't have to be this type of surface, but I also have my rooms here extruded as different extrusions. Let me hide the roof and show you this. So here I have the living room, the kitchen, hallway, laundry, bathroom, office, bedrooms, and a guest room. So every room is its own extrusion. You can model this in different ways depending on what type of project you're working on. But for a single residential home, I would say extruding each room as one extrusion is the most efficient way to work with Honeybee. If you're working on a larger project, there are other methods that might suit you better. But for this example, this is how I'm gonna do this now. So it is important that they are aligned with each other, that they are perfectly aligned, that everything is clean and smooth, no extra surfaces or curves, so you only keep the extrusions for your room, and that's it basically. So with this all set in place, I also have the whole building here as one single extrusion. So this is actually the extrusion I'm gonna use initially to show you two different ways we can analyze our site and how much sun and how much radiation our site and our building gets throughout the year. So let me first select all the things that I want to analyze, which are my buildings, the roof, and the terrain. And let me set those in one geometry container, or reference them in a geometry container. Geo to analyze. And then let me also set the shading, which are my trees, and set them in a geometry container as well, but name it into context. Okay, and then let me hide everything here in Rhino. So first off, I'm going to show you the Ladybug Solar or Direct Sun Hours, it's called, this component. So what it needs is, it needs the vectors, and we get the vectors from our SunPath component that we worked on before. So I'm just going to plug the vectors in. For this component to work correctly, you should apply an analysis period, which we already have, so I don't have to do anything. But it's important that this is connected before you use this direct sun hours component. It also needs the geometry, so I'm going to just plug in my geometry into here and the context into here. And it needs a grid size input. So the grid size is basically asking for how do you want to divide this geometry, like what type of grids do you want to divide it in. So I can divide it into a 1 meter grid for this example. And it also needs a Boolean toggle to run this component. So I'm going to connect a Boolean toggle and set this to true and see what happens. First, let me hide this. So now I get this geometry showing me how much hours of sun each point in this grid gets throughout the year, or now specifically how much it gets in March, the 21st of March. But I can change these values to, let's say, how it looks in June. Oh. Let me set this to 6. So here we see that in June it gets all this amount of sun. So the yellow parts get 19 hours of direct sun, while this part, the eastern facade, which is a bit shaded by these two trees here, it almost gets no direct sun. So we know that this part is going to be a bit chilly, which can be really nice in June maybe, but not so nice in January. So these types of results can influence how we choose to shade our site, where we choose to place our terrace, and so on and so on. So it can be very useful for those specific reasons, and it can show us where we should use some type of shading device to create a more comfortable outdoor area, for example. So that is the direct sun hours component. Let me group it and hide it for now. And let me also show you the Ladybug incident radiation component. So it needs the same inputs as we had before. It needs our geometry to analyze, a context, and a grid size. But instead of the vectors, it needs a sky matrix. It also needs a Boolean toggle, so I can set the Boolean toggle here and also connect my sky matrix that we worked on before into the input here. And set this to true. Now it's going to take some time because I didn't set an analysis period to this sky matrix, so now it's calculated for the full year. But what this is telling me is how much energy from the sun each part in this grid is getting throughout the whole year. So this can be extremely useful when we are talking about solar heat gain, in terms of where we want to place our solar panels, or where we want to place our large window openings that we want to use for passive heating, for example, and so on. So these two tools can really guide us in those decisions, giving us an idea on what the conditions are at our site. The more context we give it, the more realistic it's going to the result is going to be. So I really encourage you to work with and play around with these two tools. It's great for more urban projects as well, giving you an idea on which parts of your site is going to be a bit chilly, where it's going to be a bit too hot, where you might want to add shading, where you might don't want to have some type of seating area, and so on. So both are great tools for those types of projects. Let me group this and hide this for now, and let's continue working on our model. Okay guys, so up until this point we have mostly focused on the Ladybug components and tools, but now it's time for us to jump into Honeybee. And in order to do our energy calculations and our daylight analysis, the first thing we need to do is to set up a Honeybee model with all of our rooms in it. And there's a bunch of different ways we can do this, but in this example I'm going to show you this Honeybee room from solid component and how we set up our rooms using this component. You can also choose to set up your rooms using faces, but it's not as efficient, I would say. That's my experience, at least. So in this example, I'm going to use this component to set up and create our Honeybee model. But the first thing I need to do is to reference all my rooms in a container. So let me first select all my extrusions. Let me hide the roof, and let me hide the closed poly surface that covers the whole building, because now I'm only interested in the rooms, the extrusion of the rooms. So I can select them in this layer. So here I have the living room, the kitchen, the corridor, hallway, laundry, bathroom, office, bedroom, 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 and a guest room, and the dining room. So these are all my rooms, and as I talked about before, it's very important that they are all aligned and that it's a very simple and clean model, so it's easy for Honeybee to read it. So let me select all of these extrusions and reference them here in my geometry container. I can name this extruded rooms, for example. Let me hide them in Rhino. So now I have my rooms here, and the first thing I want to do is to use this intersect solid component, and if I hover over it, it tells me that take a list of Honeybee rooms, close preps, and split their faces to ensure that there are matching coplanar faces between them. So it just makes sure that there are matching faces between all of our rooms, basically. So I need to also set a Boolean toggle to this run input and set this to true. And now what I want to do is I want to create my rooms, basically. So, but first I want to divide my rooms so that I have control over which rooms are grouped together, because later on we will give all these rooms specific programs, and you can also give them specific constructions or thermal mass loads and all this information to make your calculations as accurate as possible. So what I want to do first is simply just organize my rooms in a way that I know which rooms are which, and basically name them as they are, what they are basically. So I will use a list item component, and since there are 12 rooms, I will create 12 separate outputs from this component. And then I will name each room the name of that specific room. So this is the dining room, for example, so I will name it the dining room, and then I will simply just do this with all of my rooms. So this is the kitchen, this is the laundry, hallway. This is the bathroom. Corridor. Office. Guest room. Last but not least is the living room. So now let's organize them a bit. So the living room is down here, and it's close to the kitchen and dining room. And we also have the corridor there, and the hallway. The bedrooms are their own group, and then this room can be their own groups as well. So now let's give all of these rooms a name. So basically I will just give them the same name as I gave them here, and connect the brep into the geometry input in the Honeybee room from solid component. And then here I can give them a specific program, a specific construction set, and a name. So for now I will only give them a name, basically. So I will do this with all my rooms. And how much you want to divide them, it's all up to you. Maybe you only want like divide them into two categories of room. You have maybe active rooms and not active rooms, or social rooms, and or whatever how you want to divide them. But as I said before, you can give each of these components a specific program and a specific construction set. So for example, the laundry maybe requires more electric, it has more electric equipments in it than the bathroom, but maybe the laundry is only used once every week. So I want to give it that specific program in order to get as accurate as energy calculation as possible. Then maybe I want to set my laundry into its own, with its own program. But sometimes it's not that important to have it that accurate. So maybe I could have put the laundry and the bathroom in the same components because they are almost the same. So yeah, it kind of depends really on what you want out of your model, basically. And here I actually want to first give these the hall and corridor can be hallways, but the kitchen I want to give its own specific program later on, so I will give it, separate it from the living room and the dining room. Living spaces. Okay, so now what we can do now is we need to use a component called solve adjacency, and it simply just identifies which rooms are adjacent to each other, and then makes sure that the internal barriers between those rooms are correctly set up in our model, so that their heat transfer between them and so on is worked in the correct way. So I will connect all my rooms into this component. But for these rooms, the hallway, the corridor, the kitchen, the living room, and the dining room, they don't have any interior walls in between them. So what I want to do with them before I connect them to this component is to connect them to their own solve adjacency component, because what this component has is this air boundary input, and if I set this to true, it will make sure that there are no interior walls between the rooms that are connected to this component. So before I connect them to the other rooms, I'm gonna separately connect them to this component, set this air boundary to true, also set the run input to true, and the same I will do here. Set the run input to true, and then I will connect the output from this from these rooms into this solve adjacency that we had before. So now all the rooms are here in this output here. So what we want to do now is we can set our windows to this model. So we first need this add subface component, and we need to connect our adjacent rooms output to the Honeybee object input, and then we need to create our windows with this aperture, Honeybee aperture, not sure if I pronounced this correct, but this component anyway. So let's go back to our Rhino file and see where our windows are. And what we can do with this component is, you see that it has this operable input where we can decide if these windows are able to be opened or not. So let me first choose the windows that are able to open, which should be this one, this one, this one, this one, this one, and this one. And this one, and this one. Actually, all of the windows except these big windows and this big windows are able to be opened. So I will set them in one geometry container, reference them here, connect them to my input here, and set this operable input to true. And then I will duplicate this and name this operable windows. I can duplicate this and select this and this window. And now I'm going to set this to false. And I also can create a door with the Honeybee door component. My door is over here. So I will reference this as well in a geometry container. Name this door. And what is very important when you set these windows and doors is that these surfaces are perfectly aligned with the room geometry that you referenced before. So if they are not, the Honeybee model will not read them correctly and it will not work. So please make sure that everything is aligned perfectly. Okay, so let me hide the door and the windows. Now I can connect these outputs here to the subfaces input. And now we can actually also set our roof here. So if I show the roof here and reference it in a new geometry container here, I name this roof. Let me hide this. Now the roof is a bit special in this design because it's closed in most rooms except this living room space where it's open. So to fix this, I can also do what we did before here with the air boundary. But to do that, I need to first separate these rooms so that I only choose my living room, since I have named them, or wait, my living room and dining room are both the same. Okay. Let me do this, and then this will only be living room, and this will only be dining room, so that it's easy for me to select only the living room now when I'm gonna do the roof. And let me connect this also to the solve adjacency here. So I want to select the living room. And now I'm gonna use this solve adjacency, but first also I should do the intersect solid with my roof, as I did before with all my rooms. And then I can select my roof with the list item component. So here is my roof now selected. I just reversed this list. And now I want to do the solve adjacency with my living room and the roof. First I need to make a room, of course, out of my roof before I connect it. And name this roof. And now I can select, so my roof is now connected to this, and then I want to connect my living room to this. And I want the air boundary to be true because, as I said, it's open between the living room and the roof. There are no ceilings there. So I'll use a Boolean toggle to run this and set this also to air boundary. And then the final step is to solve adjacency between these rooms and the other rooms that I cooled here when I chose my living room. And now this output should be all my rooms and my roof, and if everything is correct, there should be no ceiling between the living room and the roof, but there should be ceiling between the other rooms and the roof. So let me connect these rooms to the subface objects input. And to visualize all this, we can use something called Honeybee visualize by type. So I'm going to connect this output here to this input, and I'm going to hide everything else. And now you see that all these geometries actually got a color in this from this component. And we can also choose to hide this component and only show the interior walls, for example, and the walls and the ceilings. So here you see that the ceiling is now covering everything except the living room, just as we wanted. And the exterior floors, we don't have any interior floors, or maybe we do on here on the attic, but the apertures, the windows, the doors. So you see that everything seems to be set up correctly. So it has read everything exactly as we wanted it to read it. We don't have set any interior doors for this model. It's not really needed for this calculation, but if you want it to be very accurate, of course you can set up your interior doors as well. And yeah, this is how you set up a Honeybee model in Grasshopper, and or how you set up your rooms in order to later turn this into a model. So that was all for now, and in the next video I will show you, or in the next chapter I will show you how we can continue working on this model to make it even more accurate and prepare it for our energy calculations. Okay guys, so let's continue working on our Honeybee model here. So we have our rooms set here with our windows and our door openings, and everything is working correctly with the roof and everything, but now we want to add some ventilation and so on to it to make it ready for our energy calculations. So let's go to this Honeybee energy component. So in this specific example, we will rely mostly on natural ventilation for our ventilation in this building. So to set how we want our natural ventilation to function, we can use something like a window opening component. So what the window opening component needs is it needs our rooms, of course, and it also needs a ventilation control component. So with the ventilation control component, we can set within which temperatures we want these operable windows to be open, basically. So we give it a minimum interior and a maximum interior temperature and a minimum outside and maximum outside temperature. So let's give it maybe 20 to 28 as the interior temperatures, and for the outside maybe 15 to, let's say, 30. So within these temperatures our windows will be able to open for natural ventilation. And it will take into account this in our calculations later. So let's group these for now, and we can hide them. And if we go here to the HVAC subcategory here in our Honeybee Energy menu, we find all these different components. We have the ideal air, which is a great way for calculating a pretty simplified version of both heating, cooling, and ventilation within one component, but it doesn't really take into account the energy requirements that a real-world HVAC system needs. So for this specific example, it's not really useful for us. And we also have the all-air HVAC component, which if we hover over it, it says, applying all air systems provide both ventilation and satisfaction of heating plus cooling. However, because such systems often involve the cooling of air only to reheat it again, they are often more energy intensive. So in this specific example, it's not really useful for us. It's more useful for larger commercial buildings or office buildings where the need for ventilation is much higher than in this residential home. So we're not going to use this component either. And then we also have this dedicated outdoor air system, which it separates the ventilation supply from the satisfaction of heating plus cooling. So we could actually use this in our example and use it for our kitchen, for example. But to make it a bit more simple in this specific example, we are only going to use this heat cool HVAC, which only focuses on the heating and cooling of a building. And in our specific case, it's going to be only the heating of our building, because as by now, air conditioning is not really a big thing in this climate. It might be in a decade or so, but for now, it's not something that's often used. So we are only going to focus on the heating of this building. And under all of these components, we also find these templates components. So we can choose a system with this template that we want to use for our heating of our building. So down here we find one system called residential heat pump with no cooling. So this fits us perfectly for this example. So we're going to plug this into our system type, plug our room output here from the window opening component into the room's input here. And we also can give this something called apply set points. So what this gives is it tells the system on which specific temperatures we want the heating or the cooling, if we would have that, to kick in basically. So let's say we want the heating to never drop below 20 degrees. So we're going to set the 20 as the heating set point. Connect our rooms to this, and now we have a heating set for our building. We can also use, here in the HVAC, we can find things like service hot water system. We can also find the template for that, so we can choose how we want to heat our water. Let's choose a heat pump water heater as our system type and connect our rooms to it. But now you see it turned red, because we also need to tell it in which room we want this heat pump water heater to be located in. So we simply are going to drag the room where we want it to be located in. Let's say we want it in the laundry room, so we're going to drag our laundry room here into the condition input. And now this is located in the laundry room and it's heating our water for us. So let's group this now as well. And here we can also work with if we would have solar panels, for example, or yeah, a bunch of different other things here that's not really needed for this specific example. We can also use a detailed HVAC system, but for now this will work just fine for us. So let's now connect this to a Honeybee Model component to create our model. So we're going to connect it to the room's input, and here we can also connect if we have any shades, which we actually have. So let me just select these shade geometries that we have. and reference them here in a geometry component or container. And then I need to make this into a Honeybee shade object before I connect this to our model. I can group this. And now we have our model here. So let's connect our visualization to this model instead. And now it will show us the shading as well. Let me hide it in Rhino. Okay, so now we have our model completely set up here with a heating system, natural ventilation, heating of our water, and so on. So the only thing that's left for us is to give our room specific construction sets and programs in order to give to add some even more complexity and make it even more realistic when we jump into our energy calculations later on. Okay guys, so now we have our model set here. We have the natural ventilation fixed, we have the heating of the building fixed. So now let's actually go back to our room components and look at the program and the construction set for these rooms. So let's start with the program. What the program is a bunch of information telling this model how this room is going to be used in terms of people occupancy, electric equipment, lighting, and so on. So the more information we feed this model about each specific room, the more accurate the results will be. So to give a room a specific program, let's go down here and use the Honeybee search programs component. And let's also get the Honeybee building programs selector. And with this we can select from a bunch of pre-installed templates that already exist in Honeybee. So we don't find a residential home here, but we can use this mid-rise apartment template for our residential home. And then we get an output of specific room programs. So we get the mid-rise apartment, we get the mid-rise apartment corridor, and the mid-rise apartment office program. So to select one of these, we can use a list item component and a slider. And we can connect a panel to the output in order to see what program we are selecting. So we have the mid-rise apartment, the mid-rise apartment corridor, and the mid-rise apartment office. But if you do have the human plugin installed, and if you don't, I recommend you to get it because it has a bunch of useful tools and components that will help you a lot. So if you have it installed, let's instead use the item selector component, and you can just use this component to choose one of the outputs from the room program output. So let's copy this 3 times in order to select all of these programs. And now to assign a program to a room, we can either use the Honeybee apply program type component and connect all the rooms we want to apply a program to and our program to it, or we can simply just connect these programs to the room component itself when we created the room. So this is what I'm going to do now. So I'm going to use this mid-rise apartment program to most of these rooms. I'll use the office program for my office room. And I'll use the corridor program for my hallways. But other than that, I will use the apartment program. So now we have assigned a program to all of these rooms. But let's say, for example, we want to assign a specific program for the laundry room, because we know the laundry room in this family is only being used in the weekends, and it behaves quite different from an average apartment room. So we want to give it a specific program where we can set all the specific information about how this room is being used, because we think this is going to have a big impact on the final energy simulation. So in order to create a program, let's first deconstruct one of these existing program that we have in order to see what type of information it has. So to deconstruct a program, we can use this Honeybee deconstruct program type component. And let's connect the apartment program to it. And it gives us all these output of loads that make up this program. So we get the people, the lighting, the electric equipment, gas equipment, hot water, infiltration, ventilation, and set point. So we can actually deconstruct these loads also using these components here. So let's deconstruct people and electric equipment. And let's leave the others, because the others we're not gonna make changes to. Let's say we only want to make changes to the people occupancy and the equipment load itself. So we see now what type of information these loads contain, and they have a people per area, an occupancy schedule, and an activity schedule here in the people loads. So to see what the schedule is, we can actually use a deconstruct schedule component as well. Connect our occupancy schedule here, and then we get this data here, and we can use a deconstruct data component, a Ladybug deconstruct data component, in order to make this data into a list of values. And let's connect it to a panel to see what type of values it has. So we see now that this occupancy schedule in this program is containing 3 branches of data. They are all the same in this specific program, but if we look deeper into it, we see that each branch has 24 values, so each value represents a percentage of the occupancy in that hour of the day. So we see here from midnight to 6, we see that the occupancy is set at 1, so it's 100%, meaning that when people are sleeping, this room is occupied 100%. Then as the morning starts and the day comes, we see that the occupancy drops down to 0.25% when people are at work and schools and so on. But then in the evenings, it slowly goes back up to 100%. So this is what this schedule is, the type of data information that this schedule has in this template. So if we want to make changes to this, we can construct our own schedule. Using a Honeybee weekly schedule component, and using these gene pools, which are basically a bunch of sliders contained in one component. So let's make the gene count to 24, and let's go make the maximum 1 and the minimum 0 with 2 decimals in order to give it the same type of values as this schedule has. So we'll make one gene pool for the weekends and one for the weekdays. And then we're going to connect one of them to the weekend and one to the weekdays. And for holiday, we see here that if no values are input here, the schedule for Sunday will be used for all holidays, which works fine for us in this example. So for the weekend, or for the weekdays, I'm going to drag all these values down to 0. Let's say this room is never used in the weekdays. And in the weekend, it's not used in the night, but let's say from 10 to 4 it's used, the occupancy is set to 50%. So now we have a new schedule here. I can also give it a name. People occupancy laundry. And now we have a new weekly schedule here for our laundry room. So in order to create a new program, we need to use the Honeybee program type. And it has the same inputs as this deconstruct program has outputs. So it needs a name. Let's call it laundry program. And it needs a base program. So this will be used as a starting point for the new program. So all the loads from this program will be used unless we give it another set of loads, basically. So we're going to connect our apartment program into it and drag this over here. And now let's create our own people loads in order to set this new schedule to our program. So we're going to connect the schedule here to the occupancy schedule. The activity schedule, we're going to use the same because if we connect it, we see that it's set to 95 throughout the day, and it's referenced to the number of watts given off by an individual person in the room. So we're going to use the same activity schedule and the same people per area as well. But for our occupancy schedule, we're going to use this new schedule that we just created. And then we're going to connect this to the people input here. And for lighting, we're not going to make changes because it's not going to have a big impact. And we're not going to make changes to these either, but we want to make changes to the electric equipment because we do have a bunch of big electric machines in this room that requires a lot of energy. So we're going to create our own equipment loads. But instead of the watts per area set at 6, we're going to set it at maybe 200. And these we can all use the same values. But we also want to create a new schedule for this for these loads. So we are going to copy these 3. In the weekends, in the weekdays, it's also, we're going to use this 0, 0, 0, 0 schedule and name this electric or equipment laundry. And we're going to drag this values up to 100% because in these hours, the machines are being used 100%. Okay, so now this is our schedule for our electric equipment. And we can connect this to our new program type. And that is that. Now we are done with our new laundry program, so we can connect this to our laundry room. And now we have created our own customized program for this room with our own schedules. And of course, if we want to make more changes, we can do so to the lighting, to the gas equipment, hot water, infiltration, ventilation, and set point. So whenever you're working with programs and loads, there's always this balance between accuracy and how time consuming it will be to create this all these sets of data, basically. So for this example, I'm not going to make more changes to the programs. And in most cases, especially if it's early in your design phase, in your sketching, and you don't really need all this accurate simulation data, then you are probably fine using one of these templates. But if it's in a later stage in your design and you really you have all the data available to you and you want the results from your energy calculations to be as accurate as possible, then yeah, you can go ahead and create a specific program for each room and define all of these things for each specific room, basically. So you always need to find that balance on complexity and time consumption, basically. So yeah, this is how you create a program in Honeybee. And now we're going to talk more about the construction sets. Okay, so now we're going to talk a little bit about the construction set that we can assign to our rooms in order for the energy calculations to be even more accurate. So just like we did with the programs, we can choose from a bunch of pre-installed templates that already exist within Honeybee for our construction set. So to find those, we can use the Honeybee search construction set component and use a bunch of keywords in order to filter among these 257 construction sets that are available to us. But we can also use this Honeybee construction set by climate component. So with this, we need to give it a climate zone and a construction type. So we can get the Honeybee climate zone selector and select climate zone 6 for this specific project. And the construction type, we also need to get a construction type selector. And here we can choose from steel framed, wood framed, mass, or metal building. So we're going to choose the wood framed for this and connect it to the construction type input. So now we only have one construction set left after we filtered with giving it these inputs. So we have a climate zone 6 wood framed 2019 construction set. So we could just now connect this to our rooms here in the construction set input, and our calculation would use this construction set in order to calculate the energy demand and so on. But let's say we want to replace this construction set, the exterior walls and the windows within this construction set, with our own exterior walls and windows that we have chosen for this project. So to do that, we can deconstruct this construction set just like we did with the programs before, but we're going to connect this construction set here to the deconstruct construction set input, and now we get these things, these outputs. We get exterior wall, roof, floor, windows, skylight, and so on. So in order to create our own construction set, we go here to basic properties and go to Honeybee construction set component, and we can give it a name and we can give it a base construction set, just like we gave our program a base construction set, and then it will use all that information in the base construction set unless we give it something else to replace that with. So we're going to connect our construction set that we chose up here into the base construction set, but for the exterior subset and the subface subset, we want to replace those with our own exterior walls and windows. So let's go get an Honeybee exterior subset component and a subface subset component. But first, also let's get the exterior subset. So the exterior subset contains our exterior wall, that's why I got it, and the subface subset contains our windows, so that's why I got this component. The others, the interior and the ground, we can leave for now because we're not going to make changes to those. So it's going to use the base construction set that we gave it. So let's give this exterior subset a roof and a floor. And this subface subset, let's give it skylight, operable, exterior door, overhead door, and glass door. And now the things we want to change are the exterior wall and the window. So to do that, we need to create our own constructions, our own construction for this wall and for these windows. So we can go here to Honeybee construction, and You see here we have a Honeybee window construction component. So let's start with the window. And what it needs is, it needs the materials and it needs the frame. So we need to get a window material, and we need to get a window frame material component. So here we can give it a U factor, a solar heat gain coefficient, and a visible transmittance of the glazing system here. But let's give this a U factor of 0.7. Let's say we know exactly what type of windows we're going to use in this project. So we have all this data available to us. So let's give it a U factor of 0.7 and the solar heat gain coefficient of 0.5, let's say, in this example. And let's connect this to the material. And then for the frame, let's say it has a width of 0.08 and maybe a conductance of 1. And that's it. So we're going to connect this frame. Let's leave the others and connect this frame here. And now we have created our own window construction here with these inputs. And now we can connect this construction output to our window input here in our subphase subset. So now we're controlling our windows with these sliders here. And now let's do the same with the exterior wall. So let's go up here to the Honeybee opaque construction. And it needs a bunch of materials. So we are going to use a merge component and merge these materials from exterior to interior in that order. And then connect this to the materials input here. So let's go get a Honeybee opaque material component. So this will be our the most exterior of our layers. So this is going to be, let's give it a name, exterior cladding, and give it a thickness of maybe 0.02, a conductivity of maybe 0.14, a density of, let's say, 500. So we can, if we have, as I said before with the windows, if we have all these informations about the type of wall that we're going to use, we're just simply going to plug this in to these components and create our wall system here with this construction set. So that's what I'm doing here. But I'm just giving it some values here. I don't have a specific wall in mind. We can give it a roughness. Let's say this is rough. The thermal absorption, maybe. Okay, last one. We don't have to give all these inputs to the other materials, but just to show you how we could do this, merge it into the first input there. And now let's create our second layer. We don't need to create layers for like ventilated air gaps and so on. Only the layers that deals with the heat transmission, basically. So let's create a new opaque material here. And now let's give this a name, some type of wind blocker. Let's give it a thickness of 0.0. Conductivity of 0.13. Yeah, let's leave the others, and let's connect this to the second input in our merge component. So the only things that are mandatory are these with the underline before the name of the input. So let's duplicate this. Or actually, let's create an opaque no mass material for our isolation here. And then we're just gonna give it, let's give it a name, isolation, some mineral wool or something. Now we're only gonna give it an R value here, so let's give it 5. And connect this to the third input, and then for our last input we're just gonna create some type of gypsum wall here. So let's make the thickness maybe a bit thinner. Okay, so now let's say we are done here with our exterior wall, and now we can give it a name as well. Exterior wall, and connect this construction here into our exterior subset component. Oh, wrong inputs. Okay, there we go. And now we're going to connect the exterior subset here and the subface subset here. And now we are done with our construction set with our own exterior wall and our own windows that we just created. So now I'm going to connect this construction set to all of these room components. We could, of course, also use a different method to do this. That's maybe a bit faster, but now I'm already halfway through. Okay, so now all of these rooms have a construction set assigned to them, where with our own created exterior walls and our own created windows. So this was a little bit about how you can assign a program and a construction set to your rooms in order for the calculations to be more accurate. But as I said, it's always important to find this balance between time, how much time it's going to take, and how much more accurate your model will be. But for your construction set, if you have all the information available to you, maybe you're in the final steps of the project and you have chosen what type of wall, what type of windows you're going to use, then you probably already have all this information available to you, so it's not going to take that much time for you to set up the model with all that data set correct. So this was a little bit about this, and now let's move on to doing some more analyzation and some more simulations on this model that we just created. Okay guys, so let's jump into doing some daylight analysis with our model that we have created, and let's do so by first hiding this visualization component and go and get a Honeybee sensor grid from rooms component and connect our model into the rooms input, and then we need to give it a grid size. Let's give it 0.5. The distance from the floor is set to 0.8 as a default, so we can keep it at that for now. And you see here that it also creates a grid here for our ceiling, which is not really needed, and it actually covers the view a bit. So I'm gonna go and disable the roof component for this part of the simulation and just focus here on our floors. And what I need to get also is assign Honeybee assign grids and views component. So I'm going to connect the grids here to the grids input and our model to the model input. And I'm also going to use a mesh join component for our mesh output to join all the meshes into one. And now I'm going to go and get the Honeybee daylight factor component. So this is one of the most simple daylight simulation tools that we can use. It doesn't need any weather data, it just needs our model basically, and then we can give it a Boolean toggle and tell it to run basically. And it's only going to calculate the daylight factor based on the size and the location of our windows. So let's go set this to run. Okay, so we can connect the results to a panel, and you will see that the results now is divided into branches. So each branch is one room, and within these rooms, all of these values represents a grid point within these rooms. So we can use this data to calculate the median value, for example, for each room or whatever we want. But we can also connect our results to something called a heat map. So what this needs is, it needs the mesh, a join mesh, and the values flattened out. So let's connect the results and see how this looks, and let's hide everything else. So we get this heat map showing us the results in this diagram, and you can see that all of these colors represents different values from this analysis. And we can also change the colors and how this appears with this legend par input. So we can go get a legend parameter component, and here we can change the colors. Let's say we only want red and white, for example, in this heat map. So let's connect those two colors and then connect this to the legend parent input, and now you see it's only visualized with the colors white and red. So the first color we connect will represent the lowest values, and the second color will represent the higher values. And we can change things like the font and the text height and so on, and really adjust it to look in the way that we want it to look. And then we can use this heat map. We can bake it into Rhino. We can bake it into as a mesh into Rhino, and continue working with this in Illustrator or wherever we want to work with this. So let's delete the legend parameter for now and show you some more advanced tools to simulate the daylight or analyze the daylight's conditions within our model. So we can go and get a Honeybee annual daylight component. So what this needs is, it needs our model, but it also needs a weather file. So the weather file we can go and get from our EPW file. Using this Honeybee weather from EPW component. Connect our EPW file to this, and we get a weather file as the output. So let's go drag this down here and connect the weather to the input here, and it also needs a Boolean toggle to run this component. And here we can also change the threshold for this component. So by default it's set to The upper threshold is set to 3000 and the lower threshold is set to 100 lux, and the daylight autonomy threshold is set to 300. So let's keep it as its default for now, and connect the daylight autonomy results in percent to our heat map and see how this looks. So the daylight autonomy basically tells us which parts of our rooms that will be lit up by the daylight enough for no artificial lighting to be needed. Like how much percentage of the time these points within our model will be enough lit up by daylight so they don't need artificial lighting. So we also need to connect the mesh join here to the mesh input and flatten out the results from our DA output. And now we also need to run this, of course, so it's going to take a little bit longer time. Okay, so now we have the results here, and we can see that how much in percentage of each of these points within our rooms will have enough daylight so they don't need artificial lighting. So we see here that the living room in general is very well lit, so is the dining room with our large window openings here. The kitchen, not so much. So where we will mostly need artificial lighting is in this corridor, in the bathrooms and the laundry room, and a bit in the kitchen. And the office also might need quite a lot of artificial lighting because it only has this small window and it's facing the north. We can also visualize our UDI, and the UDI stands for sorry, useful daylight illuminance. So this also gives us results in percentage. So this is the percentage of the occupied hours that illuminance falls between minimum and maximum threshold. So let's connect this and see how this looks. And now it's actually looking quite good, but now we see that here close to the windows it might be actually too lit up, so it doesn't really reach the over 50% of time. But yeah, it's mostly in the corridor and the bathroom and the laundry room that we are going to be very dependent on artificial lighting. So these are some ways on how we can analyze the daylight conditions inside of our model. And let's move on to now focusing more on the energy demand within our building. Okay, so now I have grouped our daylight analysis components here and disabled them for now. I've also enabled our roof again, so everything is now visualized here in our model. And before we jump into the energy calculations, I also need to assign our roof a program and a construction set. So for the construction set, I'm going to use the same construction set that we created before, that we have assigned to all of the other rooms. For the program, I am going to try to find some type of program for an attic. So So let's see what they have in the template library. Okay, so they have a bunch of different ones here. It's not really that important. I'll just use this small office attic program. And let's hope it matches more or less an attic for a residential home. And that's it. So now let's jump into our energy simulation here. So the first thing we need to do is to go and get a Honeybee simulation output component, and we need to give a Boolean toggle to the things that we want to have as an output from this simulation. So we're going to set this to true and connect it to the zone energy use, the system energy use, the gains and losses, and the surface energy flow. And now we're going to get a simulation parameter as well. Connect the simulation output to this. Also give the time step a value of 1. And now we're going to connect this to our Honeybee Model to OSM. And OSM stands for Open Studio Model. So we're going to connect this simpar output to this. We're going to get our EPW file from here. Connect it here to the input here, and go and get our model, obviously, and connect it to this model input. And this component also needs a Boolean toggle to tell it to run and to tell it to write. And now it's going to take some time. Okay, now it's done, and we get all of these outputs from this component. So the first thing we might want to check out is the end use intensity from our building. So let's connect the SQL output to this and connect the outputs from this to the panel. So the overall end use intensity for our building is now 77. So that's a pretty decent number. But let's see what type of values that make up this value, how they are divided in different uses. So we see here that the heating takes this amount of energy, the lighting this, electric equipment takes 19, water systems 11, and so on. So it's a pretty decent result. I think we could get it down even more, especially this electric equipment, if we assign the rooms a bit more with correct programs. For example, the guest room is never being used almost, only maybe in holidays. And in weekends, some weekends, and so on. So if we go and make the programs more accurate, I'm sure we could lower this value even more. And we can also go and try to make changes to our construction sets, change materials, change maybe the floor, maybe the roof, and so on, to see if we can decrease the value for our heating as well, to keep if we can use more sustainable constructions in order to keep more of the heat inside and lower this value even more. So this is a great starting point though to have, and now it's just you can just go back, make changes, and see what effect those changes have on this value in order to achieve the most sustainable and energy efficient project that you can. So we can also use this Honeybee read room energy results component. And with this, we can divide the different loads that make up these values and visualize them in an hourly plot, for example, to see how the demand for energy looks in different times of the day and in different times of the year, which can help us guide us in our design decisions moving forward. So let me show you guys how this looks. Okay, so now let's connect this to an hourly plot. And let's say we want to visualize the natural ventilation load, for example. So here we see that in summer, when the temperatures are within the threshold for our natural ventilations to kick in, we actually lower the energy demand. And you can see how much we lower it for each specific room and every hour in the day, in every day in the month with this component. So it's really giving us a lot of information. And we can also visualize things like electric equipment, how the energy demand for that looks throughout the year. And you can see here in the laundry room, for example, where we set our own program and told it to only work in the weekends, or tell it to use the energy, the electric equipment only in the weekends. You can see here that in the weekends we have this red through those hours when we set it to function. We have these red squares, while in the rest of the time it's set to 0. So you can really see how our programs is affecting the results in this simulation. And as I mentioned many times before, the more detail and the more data we feed it, the more accurate these results will be. But for now, I think that's all for this initial energy simulation, and let's continue working with some more thermal comfort analysis and simulations moving forward. Okay, so now we have done our first initial energy simulation, and now I want to show you guys how we can continue working with this model using some of the pre-installed scripts that come with our Ladybug Honeybee installation. So to find those scripts, let's go and open a document and go to your Ladybug Tools folder where you have this samples folder. And for this specific example, let's go to the Honeybee Energy folder. And here you have a bunch of scripts pre-made for you that you can simply just pick and choose whatever simulation you want to achieve. So let's choose this single family comfort study, for example. And now I can simply just select all the components that I want to use, which in my case are everything except the EPW file and the setup for the model, because I already have my own model. So let's copy these components and paste them into our own file. And now let's drag these wires from the EPW file to our own EPW file, holding Control and Shift, and just drag them here to our EPW file output. And now we can delete this component and do the same thing with these model wires. Hold Control and Shift and drag the wires up to our own model. So now everything is set up and configured with our own model, so the only thing for me to do is to set this boolean to true and run this simulation basically. Okay, so now our results are done here. So let me go and hide this visualization component to visualize our results. So we see here that The average operative temperature in each of these rooms are visualized with a color. So we see that they are around 20 degrees because our set point is set to 20 degrees, so that's when the heating kicks in. But we also see that the laundry room is a bit warmer than the other rooms, and that's because we have placed our water heater in this room, which affects the temperature in this room. We see here that the coldest room is our dining room here, and it's a bit hard to understand why that would be the coldest room. Maybe it has to do with how our roof is set up, but we can also visualize these geometries as faces, so we can see, for example, our windows, what temperature they have, which can be quite interesting, how they affect the temperature, the comfortness in these rooms. And we can also visualize this data in an hourly plot, seeing the comfortness in each of these rooms throughout the year in different times of the day. So we see the yellow is the comfortable, the blue is when it's too cold, and the orange is when it's too hot. We also have too humid and too dry as different colors. So we can see that it's mostly comfortable. In winters it gets quite uncomfortable. It's not uncommon for homes in Sweden to be uncomfortable in winter because we have pretty harsh winters, but of course we might have to look into our construction sets or into our heating system, maybe change the set point to adjust this, because we need to find some balance between being energy efficient but also being comfortable to be inside the home, of course. So we can use these results in order to make changes to our designs in order to achieve, to find that balance between energy efficiency and comfortness. So let's group these components and hide them for now, and let me also show you another one of these sample scripts that we can use. So this is called comfort mapping. So let me open this script. And let me do the same thing as I did before, copy everything that I want to use and paste them into my own file. And let's drag this EPW component up here and replace these wires with our own EPW file and DDY file. So I can delete this. And let me also drag this these model wires to our own model. And these rooms to this grid component, because it was asking for these rooms. So now everything is set up, but I also want to add an analysis period for this component, otherwise it will take so much time. So let me get a Ladybug analysis period, and let's say I only want to analyze for the month of June on one specific day, the 21st. And connect this period to my component. And now I will run this simulation. Okay, so now it's done. So now we can get these heat maps showing how much percentage of the time it's considered to be too hot or too cold in our rooms. So we see that it's not considered to be too hot in a lot of places. It's only here in the large window openings right next to it. However, it is considered to be too cold. And this could be because of our natural ventilation, how it's set up. And we might want to have to add some thermal mass as well into this model for some better accuracy. But we can also visualize something called temperature data. So let me set this to true. And now we can actually see the specific temperature, the operative temperature in this specific day of the year, and see which temperatures that will be measured inside of our rooms. So we see that this bedroom is getting a bit hot, a bit hotter than the rest of the rooms, and that's because in summer with this big window and this window, it might make it a bit too hot. But we also see the attic is pretty hot, but that's kind of expected in a summer day. In general, it kind of lays here in between around 21, which seems pretty legit, considering that this is both day and night temperatures, and we have natural ventilation activated. So yeah, these are some components we can use, and now is when the fun begins. Now when we start making changes to our construction sets, to our designs, to our all of this data that we fed into this model in order to see how it's affecting the results in these simulations. So it can be very useful to find this balance between the thermal comfort but also the energy efficiency. So I really recommend you to go and get these plugins and start using these tools. And thank you for watching. I hope it has been useful for you, and stay tuned for more videos. Ladybug and Honeybee has so many exciting opportunities and how you can use them in order to achieve more sustainable architecture, which is something we really need at this point. So thank you for watching, and stay tuned for more videos, and I hope to see you soon.